In this video, I'll look at the hypothetical situation where trials are done one after another to compare the same pair of treatments for the same condition. The carotid endarterectomy trials discussed in the video on binary trials and spectrum of indication allow us to approximate the true relationship between an index of indication, in this case percentage stenosis, and the benefits of surgery. When trial data are not available, we can't do this, but there still is a perceived relationship and a perceived spectrum of indication. Ask a surgeon which patients would benefit from an operation and they will have an opinion about it. Their opinion on who would benefit, who would be harmed, and who would on average not be affected is their perceived spectrum of indication, and that differs from surgeon to surgeon. The goal of a research project is to more closely approximate the true spectrum of indication with the perceived ones. This shows hypothetical functions linking indication to outcome for two alternative treatments of the same condition. Treatment S could be surgical and treatment M medical. If carotid endarterectomy were under study, for example, the index of indication could be the percentage stenosis and outcome could be the stroke rate. So here on the x-axis is improving outcome, which may be fewer strokes, less disability or a longer life. The y-axis represents the spectrum of the index of indication, ranging from the left-hand end where treatment S is not indicated. For example, if carotid stenosis was 0%, no operation would be indicated. At the right-hand end are cases where treatment S is strongly indicated, so if this were carotid endarterectomy, this would be where stenosis was over 90%. Between these two extremes lies a zone of equipoise and a null point where the two lines cross. Note how I've made both lines slant down towards the right. This is because very frequently the index of indication for a surgical operation involves a measure of the severity of the disease. So worse hip pain is a stronger indication for hip replacement, worse carotid stenosis is a stronger indication for endarterectomy, or a higher malignancy potential of a tumour is a stronger indication for having it removed. This means that whatever treatment is chosen, the outcome is likely to get worse with an increasing indication for surgery, which is why both lines slope downwards towards the right-hand side of the graph. Actually, this also applies to many non-surgical questions. Suppose you're studying interventions to help unemployed people get back to work. An index might be time out of work. Whatever intervention is used, it is likely that the longer someone's been out of work, the more difficult it will be for them to find a job. These are simplified straight lines. I'll show you some real ones later. Now imagine that we have a God's eye view and that these are true relationships between the index of indication for surgery and outcome for the two treatments. We are looking down on a team of researchers trying to work out what these relationships are. Our researchers plan to run a trial. They confer, consult available evidence and take opinion from surgeons. They find the opinion of surgeons about the strength of the argument for an operation depends on an index such as the percentage carotid stenosis. They find areas where there is broad consensus that the operation should be done, where it should not be done, and in between they find an area of equipoise where they consider it ethical to randomise. They therefore set up the trial. Now, with our God's eye view of the real functions, we can see what the results will be. The researchers don't know where the lines are, but they will find that the trial is positive for surgery. Their estimation of the zone of equipoise was wrong. It was too pessimistic for surgery. After the trial, the researchers wonder if surgery may be of benefit in cases they had previously not considered it for. After further consultation in the light of their trial result, they design a new trial with a new zone of equipoise. We can see that this time the result will be negative. Now, with two trials in hand, the researchers may go on to perform a further trial. If so, then the zone of equipoise will be something like this, between the previous zones. Remember that the point where the two lines cross is called the null point. Notice from these hypothetical trials that the results of a trial moves the zone of equipoise from its pre-trial position towards the null point, whatever side of the null point it started on. Let's look at a final example of two lines that do not cross. In other words, one of the treatments is always inferior. Again, we know this, but our researchers don't. They go through the same process. This time their first trial result is negative. This shows that their zone of equipoise was too optimistic for surgery. They therefore design another trial with the zone of equipoise further towards the strong indication for surgery end of the spectrum. The result is again negative. Ultimately, after enough trials, the inferior treatment will be abandoned altogether. So this is the effect of a series of trials done on the same clinical question. They cause the zone of equipoise to converge on the true null point, if there is a null point. Such a series of trials may overshoot the null point, and in principle a long series of such trials may overshoot it several times, but every overshoot will be smaller than the last overshoot on the same side, so that the zone of equipoise will always converge on the null point. If there is no null point, the series of trials allow equipoise progressively to move in favour of the better treatment until the other is forced out altogether. This would happen even if at the beginning of a series of trials the inferior treatment could not be tested in some patients for ethical reasons because everybody believed it to be beneficial. Serial trials result in a shift in the zone of equipoise that is always towards the null point. This is a necessary and sufficient condition to establish negative feedback that operates on the zone of equipoise to centre it on the true null point. As promised, I'll give you a couple of real-life treatment function pairs. This first one is from an analysis of the benefits of operating on unruptured brain aneurysms. Here the outcome variable is remaining life expectancy and the index of indication is age at the time of treatment. As before, both lines slope downwards towards the right, because the older you are, the less long you have left to live. In this case, the indication for surgery is stronger at young ages, falling to a null point just after the age of 60 and becoming negative thereafter. This is because the risk of surgery rises with age and the benefit falls because the risk posed by an untreated aneurysm is a relatively fixed annual rate of hemorrhage. The total risk of hemorrhage in your remaining lifetime therefore falls the fewer years you have left to live. This second example is from the STITCH trial, which compared surgical removal of brain hemorrhages with medical treatment, or in other words, waiting for natural recovery. It shows that for small hemorrhages, surgery is harmful, and there is a null point with hemorrhage volumes just over 20 mils. Thereafter, the benefit from surgery rises with larger hemorrhages. The reason that surgery is worse for small clots is that there is a fairly fixed risk from surgery, but the benefit is dependent on clot volume. It's only when clots get past a certain size that that benefit starts to outweigh the risk. So these two function pairs illustrate that these functions do exist in real life, though as expected they are not straight lines.